Okay, we continue with this 7.4, doing number 16, integral from 0 to 1 of x cubed minus 4x minus 10 over x squared minus x minus 6 dx. Now, notice that this is not a proper integral, a proper rational expression. So I will divide first x cubed minus 4x minus 10 over x squared minus x minus 6. What will that be? That's x cubed plus 0x squared minus 4x minus 10. And I get x squared minus x minus 6. So I have x for x cubed minus x squared minus 6x. When I subtract, of course, remember you need to change the sign. You get x squared plus 2x minus 10. X squared to x squared one time, so it's plus 1. Here I get x squared minus x minus 6. When I subtract, I get 3x minus 4. So this is equal to x plus 1 plus 3x minus 4 over x squared minus x minus 6. Now then I will do partial fraction decomposition on the last term. So 3x minus 4 over that x squared minus x minus 6. I need to factor it first though. Okay, that's 3x minus 4 over x minus 3, x plus 2. Notice that the denominator is linear factors without repetition. The denominator is our linear factors without repetition. So the denominators will have x minus 3 and x plus 2, and the numerator will be 1 degree less. So it must be a constant here, and there's another constant here. Okay, that's our 3x minus 4 over x minus 3, x plus 2. Now multiply by the LCD. Multiply by the LCD, x minus 3, x plus 2. That will give me 3x minus 4 equals to a times x plus 2 plus b times x minus 3. So I will use technique number 2, the special numbers. Okay, special critical numbers. So x equals to -2, for example. So 3 times -2 minus 4 equals to 0 plus b times -5. So -10 equals to -5b. b equals to 2. Second special numbers, x equals to 3. So 3 times 3 minus 4 equals to a times 5 plus 0. So what's that? That's 5 equals to 5a. So a equals to 1. So now we have 3x minus 4 over x squared minus x minus 6 is decomposed into 1 over x minus 3 plus 2 over x plus 2. Now let's go back to the integral. So the integral from 0 to 1 of x cubed minus 4x minus 10 over x squared minus x minus 6 dx. This is equal to integral from 0 to 1 of, what's the quotient again? The quotient is x plus 1 plus 1 over x minus 3 plus 2 over x plus 2 dx. Okay, now from there, I believe you can integrate yourself. Okay, I just do this for formality, but I do expect you are able to do it yourself. This is 1/2 x squared plus x plus natural log of absolute x minus 3 plus 2 natural log of absolute x plus 2 for 0 to 1. When x equals to 1, that's 1/2 plus 1 plus natural log of 2 plus 2 natural log of 3 minus, when x is 0, that will be plus 0 plus 0 plus natural log of 3 plus 2 natural log of 2. Which will be 3 over 2 plus natural log of 3 minus natural log of 2. So 3 over 2, 1.5 plus natural log of 3 over 2. That's the exact solution. Let's try number 18. Yeah, today I plan to just do a lot of problems from this section here. Number 18. Integral of x squared plus 2x minus 1 big over x cubed minus x dx. It's already proper. It's already proper rational expression in the integrand, so I can do partial fraction decomposition right away. Partial fraction decomposition. So we have x squared plus 2x minus 1 over x cubed minus x. And I get a message. How do you know that it's already proper? The degree on the top is less than the degree at the bottom. The degree on the top is degree of 2, the bottom is degree of 3. So it's already proper. Okay? Yeah. If the degree on the top is equal or more than the degree at the bottom, like the one we have above here, then it's improper, therefore we divide it first. Okay? In other words, if it is improper, all you need to do is actually divide it. When you divide, you will get the polynomial and a rational expression, which is proper. Now then, when you do partial fraction decomposition, you do partial fraction decomposition on the proper part. Okay? Now let's go back. Here, let me factor this. This is equals to x squared plus 2x minus 1. At the bottom, I factor the x. I get x squared minus 1, which is x plus 1, x minus 1. So this will be x plus something over x plus 1 plus something over x minus 1. And the degree on the top should be 1 less than the degree at the bottom. multiplying by the LCD, which is multiplying by the LCD, which is x plus 1, x minus 1. That will give me x squared plus 2x minus 1. That's the denominator, right, for the original rational expression. And this will be a times x plus 1, x minus 1, plus b times x minus 1, plus c times x plus 1. Now, with that said, then let me ask you to find the value of a, b, c by using the special value method. So the first one you can use is when x equals 0, what happened when x equals to 1, and when x equals to negative 1. Those are the zeros of the denominator. Okay, let me give you maybe 3 minutes for this. When x equals 0, the left-hand side is negative 1. The right-hand side is negative a. Is it right? And the second term is 0. The third term is also 0 because the x equals 0. Now from there we see that a equals to 1. When x equals to 1, we get 1 plus 2 minus 1 equals to 0 plus 0 plus 2c. Is it right? When x equals to 1, we get 2c, which then 2 equals to 2c, therefore c is equal to 1. When x is negative 1, this is 1 minus 2 minus 1 equals to, when x equals to negative 1, this is 0. That's 2b plus 0. Am I right? So negative 2 equals to 2b, therefore b is equals to negative 1. So x squared plus 2x minus 1 over x times x plus 1 times x minus 1 is equal to a over x. Now make sure you match this though, the a for this, b for x plus 1, and c for x minus 1. Okay, so the a is 1 over x, the b is negative 1 over x plus 1, and the c is 1 over x minus 1. Now, once we're done with the partial fraction decomposition, then we go back to the integral. Integral of x squared plus 2x minus 1 over x cubed minus x of dx, that's equals to integral of 1 over x minus 1 over x plus 1 plus 1 over x minus 1. Okay, dx, which then give us natural log of absolute of x minus natural log of absolute of x plus 1 plus natural log of absolute x minus 1 plus constant, which I believe we can combine together becomes natural log of the absolute of x times x minus 1 over x plus 1. Don't forget this constant. Even though I have to say that sometimes, actually all the time, this is also acceptable. Okay, either one of those are acceptable. this is the case when the denominator consists of distinct linear factors without repetition. Let's see what happens if we have the denominator is linear factors with repetition. Idea. Through an example. Suppose, for example, I have blah, blah, blah over x squared and then x plus 2 cubed, something like that. Okay? Suppose we have something like that. Then here's the thing. Here's the thing. Oh, what happened? Here's the thing. Because x has degree of 2, then we start from degree of 1 over x, but up to that exponent squared. Now, the numerator later on will be 1 degree less. Now, this one here, because even though it's degree of 2, but it's actually a partition from that x, right? So you still get 1 degree less from that x only, not from the x squared. Continue on. For x plus 2 to the power of 3, we will have x plus 2, x plus 2 squared, x plus 2 cubed. Okay, and the numerator will be 1 degree less, including the one you repeat. Only 1 degree less from that x plus 2, not from x plus 2 squared. 1 degree less from x plus 2, not x plus 2 cubed. That's the idea. Okay, let's do it. Question. Are we always adding this? Well, later on you will get your A, B, C, D, E. Some of them may be negative coefficients. So for now we use addition. For now we use addition until we get the coefficients, maybe the A, B, C, D, or E, maybe some of them negative. Okay.
So is this like an alternative, or is it used for different types of problems?
Different type. The one we get earlier, we have linear factors without repetition.
Yeah.
Right now, if it is repetition, then you need to repeat it. Right? If it's squared, then you need to repeat it twice. If it is cubed, you need to repeat it 3 times with different exponents up to the degree.
Okay.
Okay. Now, let's say, for example, we take a look on number 20. We will focus on the technique more than just the integral. You will see the integration is not doable without the technique, though. We have to do the partial fraction decomposition. Okay, so here they already factor for us 2x plus 1, and then we have x minus 2 squared dx. So I will apply partial fraction. Oh, hold on. Oh yeah, that's right. The bottom already degree of 3. Partial fraction decomposition on the top. We have this. At the bottom, we have 2x plus 1, x minus 2 squared. It's equals to something over 2x plus 1, right? You see that the denominator is linear, degree of 1, so the numerator has to be a constant, plus. And for x minus 2 factor, it has degree of 2, so I need to have x minus 2 squared. Okay, but the numerator then will be b and then c, 1 degree less. We will do the same procedure. I will multiply by the LCD to get rid of the denominators actually, right? We multiply by 2x plus 1 x minus 2 squared, such that we get on the left hand side x squared minus 5x plus 16. On the right hand side I will get a times x minus 2 squared plus b times x minus 2 2x plus 1 plus c times 2x plus 1. Now here we get some little issue. What kind of issue? Notice that we only have two special numbers. We only have two special numbers, x equals to 2 and x equals to negative 1/2. Is it right? We only have two special numbers. You can use this though. You still can use that special numbers. So when x equals to 2, I will get 4 minus 10 plus 16 equals to, this is 0, this is 0, this is 5c. So 10 equals to 5c, so c equals to 2. When x equals negative 1/2, so negative 1/2 squared is, let me write it down. This will be a times negative 1/2 minus 2 squared plus 0 plus 0. This is 1/4 plus 5/2 plus 16 equals to 25 over 4a. 64 plus 10, 74, 75. So that's 75 over 4 equals to 25 over 4a. From there we get a equals to 3. See, we have, the thing is we have only two special values, two special numbers, and using these two special numbers, we get only two variables, a and c in this case, not the b. So Thomas, how do we get the b? Well, you can choose other numbers. You can choose other numbers. Okay. From here, you can choose other numbers. Let's say I choose x equals to 3. So method 1, to find b, the first alternative to find b, I can still use method b, method 2, the special numbers. Okay, let's say I choose x equals to 1. X equals to, let's say x equals to 1. So when x equals to 1, on the left-hand side, I get 1 minus 5 plus 16, right? When you plug in x equals to 1. Now, on the right-hand side, when x equals to 1, I get a minus 3b plus 3c. Let me plug that in so that you see what actually happened. So a times 1 minus 2 squared plus b times 1 minus 2, 2 plus 1, plus c times 2 plus 1. That's a minus 3b plus 3c. And the right hand side, that's 12. Now, at the same time, we know the a is 3 and the c is 2, right? So 12 equals to 9 minus 3b. So the b, therefore, is negative 1. So from there, we say, so x squared minus 5x plus 16 over 2x plus 1 times x minus 2 squared is equal to, what is my a? My a corresponds to 2x plus 1. My a is 3 over 2x plus 1 minus b, which is negative 1 minus 1 over x minus 2. And my c is 2. Oh. Yeah, my c is 2. So plus 2 over x minus 2 squared. So I hope from this example, you see that it doesn't have to be addition, all addition at the end, but from the variable, I'm sorry, from the ABC, like in this case, the b is negative, therefore it becomes subtraction. Okay, now that's the end of partial fraction decomposition. Go on with the integral. X squared, integral of x squared minus 5x plus 16 over 2x plus 1 x minus 2 squared dx is equal to the integral of 3 over 2x plus 1 minus 1 over x minus 2 plus 2 over x minus 2 squared dx. Then this will be 3 over 2 natural log of 2x plus 1 minus natural log of x absolute of x minus 2 plus, what is this, negative 2 over x minus 2, I think. Don't forget, plus constant. Okay, I think that's simple enough. So let me just put them together. This is the final answer. But the last step here, the integration part, is something we assume you know what to do. Okay, we assume you know what to do for that one. It's the focus will be on the partial fraction decomposition. Now let me ask you to try number 22. We do a lot of problems here. Number 22. Now they use s there. I don't like it. Let me change that to x. Integral of dx over x squared times x minus 1 squared. So what you need to do is the partial fraction decomposition of 1 over x squared, x minus 1 squared. Now you need to know how to break it up though. That's the thing. You need to know how to break it down. Oh, you know what? I'm sorry. I forgot one thing. Let me go back here. Here I only show you method number 2 to find B. I only show you method number 2. Now let me combine that with method number 1. What is method number 1? Method number 1 is you choose which term you want to look at. Okay, let me do it here. So to find B, using method number 1, the combining like terms method. Okay, now, but then you have x squared, coefficient of x squared, or coefficient of x to look at, or the constant to look at. Now, you kind of like think about, okay, which one is easiest to see? For example, in this case, the coefficient of x squared is easiest to see, x squared term. On the left-hand side, the coefficient is 1, right? On the right-hand side, the coefficient is a plus 2b plus 2c, right? It's a plus 2b plus 2c. You see that? Thomas, how do you know you do x squared term? Well, it's actually up to you. You can do the x term. You can do the constant term also. Depends on which one you think is easier. Okay. Now then, when we already know that the a is 3 and the c is 2. Fast forward, you will see b equals to -1. Huh? Do I get it right? Oh, I make some mistake somewhere. That's not true though. X squared 2bx squared. Oh, no, my bad. The last one is not. Plus 0c. Yeah, because this is 2cx, not 2cx squared. Duh. Okay, so it's even easier, huh? So b is -1. Okay, so the same result with what we get in method 2. So you see, then at the in the long run, it's about the combination between method 1, method 2, whichever you feel more comfortable to play with. Okay, let me give you this problem to work on. How many minutes? Just to do the partial fraction decomposition. Maybe 5 minutes from now. 8:05. Anything, I assume you don't. A over x plus b over x squared plus c over x minus 1 plus d over x minus 1 squared. Okay, somebody say need more time. Let me give you more time. And multiply by the LCD, which is x squared, x minus 1 squared. I will get 1 equals to ax, x minus 1 squared, plus b times x minus 1 squared, plus c x squared, x minus 1, plus dx squared. Now, notice that we have 4 a, b, c, d, 4 variables to look for, yet we only have 2 special numbers. So the other 2 numbers later on, either you do, you have to be creative. Do we disregard the x? No, I don't think I did. The bx? No, because when you multiply this term by x squared, x minus 1 squared, the x squared cancels. Right? Can you imagine it? B over x squared times x squared, x minus 1 squared. The x squared cancels, right? So I get b times x minus 1 squared. You see that? Okay, now then, let me continue. So let's say x equals to 0. When x equals to 0, I get 1 equals to 0 plus b plus 0 plus 0. Oh, we get b equals to 1. When x equals to 1, 1, that's 0, this is 0, this is 0, this is d. So d also equals to 1. Now the thing is how to find A, how to find C. Now, then we have some methods that you can use. For example, if you want to look at the degree of 3, I think degree of 3 will not do. Maybe, maybe not. Or get another number. Let's say x equals to 2. So when x equals to 2, I'll get 1 equals to, when x equals to 2, that's 2 times 1 squared. That's d times 1 squared. That's c times 2 squared times 1. That's d times 2 squared. So that's 2a plus b plus 4c plus 4d. So I plug in the a, no, I don't know the a. So that's 2a plus 1 plus 4c plus 4. Let's make the 4 again. Let's pick another one. Let's say I pick x equals to -1. Why not? When x equals to -1, that will be 1 equals to a times -1 times -2 squared plus b times -2 squared plus c times -1 squared times -2 plus d times -2 squared. Negative 4a plus 4b minus 2c plus 4d. My b is 1, my d also 1. So 4a plus 4 minus 2c plus 4, 7. That's -7 equals to -4a minus c. Let me simplify that a little bit. Let me call this equation 1. Let me call this equation 2. Equation 1, I get a plus 2c equals to -2. I reduce by 2. Okay, and then equation 2 for a plus, actually I don't need -4a, -4a minus 2c equals to -7. Right? That's equation 2. So when I add, I get -3a equals to -9, a equals to 3. If a equals to 3, then c will be 2c is -5, c is -5/2. Okay, so now I have that complete a equals to 3, b equals to 1, c equals -5/2, d equals to 1. Can you find A and C using other method? Yes, you can. Yes, you can. Another method that I had in mind is looking at degree of 3. When we have x cubed, for example, so other method. When I see x cubed term, on the left-hand side, the x cubed term is 0. But the right-hand side, it's A plus C. Is it? Yeah, it's A plus C. But hold on, something not right there. Do I make a mistake somewhere? Let me see. I somehow think I make a mistake somewhere. Give me a second. Give me a second. I make mistake here. I make mistake here. Here, I make mistake here. When my x is -1, it's supposed to be -1 squared here. Let me use red color so that you see my mistake better. So that's -1 squared. So that will be just d, and this should be 1. 5 minus 1, so that's -4 here. Oh, that's even better now. So this is -4. So A equals to 2 instead. Now if A equals to 2, then C will be -2. Yeah, good thing you asked me to check it. I was actually trying to do other method too. But can you see the x cubed term here? The x cubed term on the left-hand side, x cubed term, you don't have x cubed term, right? On the left-hand side. That's why it's 0. Now, on the right-hand side, x cubed term only comes from A. We have x cubed here. The B have x squared, the maximum. The C have x cubed. The D has x squared, the maximum. Okay. Now you can also look at, for example, I think I will look at the constant. Is it possible? Yeah, let me look at the constant. Oh yeah, the constant term. The constant term on the left-hand side, the constant term is 1. On the right-hand side, the constant term is, you see, you must have an x here, right? The constant term here is b, because you have +1 times b, that's b. Now the constant term for this one here, nothing, right? Because we always have x squared, and we always have x squared here. So actually from there we get the b equals to 1, but we already know the b. But we already know the bad thing about the like terms method is you have to combine them first to see, oh, you know what, does it work or not? Okay, the x cubed term is easy to see, right? Okay, the x cubed term is easy to see. What you can do, however, is you combine what we have earlier. Let me go back all the way. You can combine what we have earlier. For example, instead of you finding this, you can use this as your second equation here. So instead of that, we use the first equation, a plus 2c equals to -2. And the second equation, a plus c is equals to 0. You see what I mean? Okay, the first equation coming from a special value, special numbers. The second equation here from combining like terms. If I subtract, I get c equals to -2. Bang, right away. And then from there you can use find the a. Okay, now that's for the partial fraction decomposition. Now go back to the question. So 1 over x squared, x minus 1 squared equals to 2 over x plus 1 over x squared minus 2 over x minus 1 plus 1 over x minus 1 squared. And therefore, the integral of dx x squared x minus 1 squared equals to integral of 2 over x plus 1 over x squared minus 2 over x minus 1 plus 1 over x minus 1 squared dx. Which will be 2 natural log of absolute of x minus 1 over x minus 2 natural log of x minus 1 minus 1 over x minus 1 squared. Actually, 1/2. See that? No. No, I don't need that square here. I don't need that square here. Plus constant. Of course, you can combine this if you want, but you can just leave it there. Okay. Let's take a break. We come back at 8:35. And once we get to 8:35, now the third part, it's a very long section, huh? Yeah, the third part, irreducible factors, to be more precise, quadratic factors, without repetition. Now, the idea is, suppose we have something over x times x squared plus 3, for example. Now then, this will be broken into, so you see no repetition, right? No repetition for the linear factors. Maybe I put x cubed here, why not? Okay, so for that x cubed, I will have something over x, something over x squared, something over x cubed. And each one of them is constant because they're basically repetition from x cubed. Now plus something over x squared plus 3, which is not factorable. Okay. Now because that's degree of 2, then on the top it should be degree of 1. Okay, so what we learned before still apply though. What we learned before still apply. For this a, b, c would also be 1 less than degree than x. Yes, because this x squared and x cubed here actually repetition from x. Okay, so it's 1 degree less than degree of 1x. Now let's do a problem right away. Let's say we do number 24. Number 24, we have integral of x squared minus x plus 6 over, let me factor it out of the way, x times x squared plus 3 dx. Now then when I do partial fraction decomposition, I have the habit when I do the partial fraction decomposition, I write this down. That's my habit. Okay, do you have to do that? No, you don't have to. But it's kind of like organizing my work so that my reader, you in this case, knows know what I do. Okay, what I'm doing there. At least you know that I'm doing partial fraction decomposition. If you don't get how I do it, then that's another story. It's x squared plus 3. So this must be something over x plus something over x squared plus 3. 1 degree less, because that's degree of 2 at the bottom, then on the top that will be degree of 1. Now from here the technique is the same, is similar, multiplied by the LCD, which is x times x squared plus 3. That will give me x squared minus x plus 6 equals to a times x squared plus 3 plus b, plus x times bx plus c. Now, the further you go into next level, in this case irreducible, then you may need to combine the special factor and the combining like terms method. Okay, let's say, for example, one special value is x equals to 0. So I get x equals to 3a plus 0. From there, we see that the a equals to 2. Can I use x equals to 1, Thomas? Yes, you can. Yes, you can. But if you take a look, for example, like terms, right? When you use method 1, x squared term. What is the coefficient on the left-hand side? 1, right? What happened on the right-hand side? The coefficient of x squared will be a plus b, right? Okay, but from there, then you see a equals to 2, so b must be negative 1. Okay, and for some coincidence, when you see x term, on the left-hand side, x term is negative 1. The coefficient of x term is negative 1. And on the right-hand side, strangely and nicely, the coefficient for x is only c. Don't you think it's so nice? Right? If you FOIL that, imagine if you FOIL this here, you will get ax squared plus 3a plus bx squared plus cx. So the only constant is 3a, and the only x term is this one. That's the only one. You see what I mean? Okay, now with that said then, so x squared minus x plus 6 over x times x squared plus 3 is equal to 2 over x plus actually negative x minus 1 over x squared plus 3. Or we can say that's 2 over x minus x plus 1 over x squared plus 3. Okay. Now, furthermore, going back to the integral of x squared minus x plus 6 over x cubed plus 3x dx therefore equals to integral of 2 over x minus x plus 1 over x squared plus 3. Okay, which is equals to 2 natural log of absolute x minus, unfortunately, I don't know how to integrate this until I separate them. Now from here, the better you memorize, the better. Is there a name for method for which you used to find B and C? Like terms method. Method number 1. From what I taught you last time, that's method number 1. So you look at the term by term, x squared term, what's the coefficient on the left, what's the coefficient on the right, x term, what's the coefficient on the left, the coefficient on the right, and so on and so forth. Okay, then from here, I will do u substitution, I guess. So u equals to x squared plus 3. So du equals to 2x dx. So the integral there will be 1/2 integral du over u minus. Do you remember how to integrate this? What is the a in this case? Square root of 3? Maybe I prefer to ask you this. Do you remember what is the integral of dx over x squared plus a squared? I wonder if you remember that. If you memorize that, that's better. Otherwise, then you need to use trig substitution. This is 1 over a tangent inverse of x over a plus constant. Okay, so with that knowledge, with that memorization, you can do this computation a lot faster. This is 1 over radical 3 tangent inverse of x over square root of 3. I don't need to use plus constant yet because I'm not done with this integration yet. Okay, but once I'm done with that integration, then I need to use that. I need to use that plus constant plus u, but now u is ln absolute of u, right? But now u is this. Number 28. Integral of x squared minus 2x minus 1 over x minus 1 squared, x squared plus 1 dx. Partial fraction decomposition. X squared minus 2x minus 1 over x minus 1 squared, x squared plus 1 equals 2. So we see x minus 1 is linear with multiplicity of 2. Right? So I need to have x minus 1, x minus 1 squared. You see that if you have repetition? Okay, while for the irreducible part, there's no repetition, so I just need one of them. But on the top, the degree will be 1 less than. I hope you copy that down. And then I go on, multiply by the LCD. Times x minus 1 squared, x squared plus 1. We get x squared minus 2x minus 1 equals to a times x minus 1 plus b times x squared plus 1 plus cx plus d times x minus 1 squared. Ooh, that's ugly. Unfortunately, we have only one special factor here, special number value here, x equals to 1, right? When x equals to 1, we get 1 minus 2 minus 1 equals to 0 plus 2b plus 0. Negative 2 equals to 2b, therefore b equals to negative 1. Now, of course, you can try what happened when x equals to 0. I think, yeah, when x equals to 0, we can get something nice. When x equals to 0, I get 0 minus 0 minus 1 equals to negative a. When x equals 0 plus b. When x equals 0 plus d. Now we know the b is negative 1. So negative a plus d equals to 0. Call that equation 1. We may use that. We will use that later on. Now let's see, for example, when we do combining like terms. Why didn't you multiply a by x squared plus 1? You are right. I'm missing it badly, huh? I'm missing it badly. You are right. Thank you. Thank you. That's really bad. Oh, I'm missing it so badly. I need to erase all of this though. I need to erase this. Give me a second. I need to erase this. To here. I need to erase this. I'm missing something here. You're right. Thank you. So that's x squared plus 1 here. Yeah, thank you. So then when x equals to 1, it really messed up everything, huh? Oh, that's 0 anyway for this. So this is 2b and this is 0. So negative 2 equals to 2b, therefore b still negative 1. Okay, but when x equals to 0, the story gets different. When x equals to 0, I get 0 minus 0 minus 1 equals to negative a plus b plus b. So 0 equals to negative a plus b. Call that equation 1. I still get the same thing, but I start with the wrong equation on the top though. By the way, should we look at the x cubed? I wonder if it helps. Yeah, so x cubed term, the left hand side 0, right? The coefficient of x cubed is 0. On the right hand side, I get a plus c. Still doesn't help. Still doesn't. If I can get something with b, that would be nice. Is there anything else that we do? How about x squared? Yeah, x squared term. By the way, this what I do here are not the only ways. Okay, you can choose x equals to negative 1 if you want. X squared term, the left hand side is 1, the right hand side is what? It's harder to see. The right hand side is negative a plus b. Yeah, it's harder to see. I don't really want to do that. Negative 2c. Yeah, it's harder to see. I don't want to do that. I try to find something that I can do it by visually. Let's do one more then. Let's say when x equals to 2, maybe. When x equals to 2, I get 2 squared minus 2 times 2 minus 1 equals to, when x equals to 2, I will get a times 1 times 5 plus 5b times 5 plus 2c plus d times 1 squared. So this is negative 1 equals to 5a plus 5b plus 2c plus d. I don't think it is e any better, but oh, you know what? You know what? I can get this. I can get this. I can do substitution. This is equation 1, this is equation 2. So from here we see that a equals, d equals to negative a. D equals to negative a. I'm sorry, d equals to a, and c equals to negative a. Do you see that? Right? This is from equation 1, this is from equation 2, up there. So let me substitute that. So this is 5a, the b is negative 1, the c is negative a, the d is a. That's 4 equals to 6 minus the 4a. So a equals to 1. Therefore, c equals to -1 and d equals to. So x squared minus 2x minus 1 over, what's that again? X minus 1 squared, and then x squared plus 1 equals to 1 over x minus 1. Where's my d? -1. -1 over x minus 1 squared. Okay, plus -x plus 1 over x squared plus 1. Therefore, the integral of x squared minus 2x minus 1 over x minus 1 squared x squared plus 1 of dx equals to integral of 1 over x minus 1, that's easy, minus 1 over x minus 1 squared, that's easy, plus -x plus 1 over x squared plus 1 dx. Okay. Then this is equals to natural log of absolute x minus 1 plus 1 over x minus 1 minus integral of x over x squared plus 1 dx plus integral of 1 over x squared plus 1 dx. Okay, with some little substitution, the third term can be done easily. X minus 1/2 natural log of x squared plus 1. And the last one here is tangent inverse of x. Just constant. Now, sometimes some problem is so sneaky such that you need to think outside the box before you actually start everything. Just give you some warning. You get so pissed off if you know that the way you do the following question has pretty much nothing to do with what we have done in the whole section today. Okay. Number 36. Integral of x to the 4th plus 3x squared plus 1 over x to the 5th plus 5x cubed plus 5x dx. Why I say so? Because this can be done so easily by simple substitution. Let u equals to x to the 5th plus 5x cubed plus 5x du is 5x to the 4th plus 15x squared plus 5, which dx, which if I factor the 5, I get the term on the numerator. You see what I mean? Okay, so all of a sudden this is equal to du over 5u, right? Which is 1/5 natural log of absolute u plus constant, which is 1/5 of natural log of x to the 5th plus 5x cubed plus 5x plus constant. Now, the last part before we go on to more sneaky method to do this problem, this type of problem. What happens if we have case number 4? Irreducible with repetition, irreducible quadratic factors. With repetition. Idea. If you have, for example, something over, let's say, x squared plus 3 squared, just like before, if you have repetition, then you need to repeat it. Like that. Okay, you have to repeat it. And then on the numerator, the degree must be less than the denominator without repetition. So this would be ax plus b. This is cx plus d. Okay. Let's see. I see only one question like that in our textbook, though. Number 26. Integral of x squared plus x plus 1 over x squared plus 1 being squared dx. So partial fraction decomposition, x squared plus x plus 1 over x squared plus 1 squared. We get x squared plus 1. We get x squared plus 1 squared here. And here I have ax plus b. The second fractions, because it's repetition, let's see x plus b. Now then, from there I multiply by the LCD, multiplied by x squared plus 1 squared. Then I get x squared plus x plus 1 equals to ax plus b, x squared plus 1 plus cx plus d. Now, when it comes to this type of equation, method number one, in my opinion, is better. Method number one is, in my opinion, is better. Let me FOIL this first. This is ax cubed plus ax plus bx squared plus b plus cx plus d. You see the x cubed term, 0 on the left hand side, a on the right hand side. Bang, you are done for a, right? Okay, how about for x squared term? For x squared term, that's 1 on the left hand side, that's b on the right hand side. Do you notice that it's actually easier doing it this way? How about the x term? The x term, 1 here on the right hand side, the x term will be a plus c, but the a equals to 0. But the a equals to 0. So c equals to 1. Right? And for the constant, on the left hand side, that's 1. On the right hand side, that's b plus d. But we know b equals to 1. So d must be 0. Therefore, our x squared plus x plus 1 over x squared plus 1 squared is equal to 1 over x squared plus 1, I love it so much, plus x over x squared plus 1 being squared. Oh, I can use u substitution for that. X squared plus x plus 1 over x squared plus 1 squared dx is integral of 1 over x squared plus 1 plus x over x squared plus 1 being squared dx. This is tangent inverse of x. Okay, the one here, if I use u substitution, that's u equals to x squared plus 1, so du is 2x dx. So okay, this is plus 1/2 integral u to the power of negative 2 du. Which is tangent inverse x minus 1/2 1 over u, negative 1 over 2u plus c. And put that back in 1 over 2 times x squared plus 1 plus constant. That's a very long section, huh? Like if you think about it, for the last 2 hours approximately, we only do how many problems? right? Why? Because the partial fraction decomposition takes some time. Okay, not to say the multiplication. It's giving me a headache. Well, welcome to calculus 2. Okay, once you get used to it, then you are much better than a lot of people. Keep that in mind. Okay. Now, let's see one more example regarding this. I saw number 30. I see number 30 seems to be quite interesting. It's easier than integration by parts. Yeah, it's just tedious. To be more precise, it's tedious. It's long, but not hard. I agree with you, it's not hard, but it's long. It's long. Of course, what you see here, just the foundation for integration by partial fraction decomposition, right? But later on in 7.5, that's why today I will not do 7.5. 7.5, which we will do on Wednesday, is technique of integration. Basically, whatever techniques that you have learned so far, put together in that one section. Let's see number 30. Let's see number 30. Integral of 3x squared plus x plus 4 over x to the 4th plus 3x squared plus 2 dx. If I'm mean, then I may say it in the very nasty way, you know, integration by parts only for adults. If you cannot handle fractions and you cannot handle rational expression, adding and subtracting a rational expression, solving system of equations, then you won't be able to do it. That's if I say it in a negative way, in the nasty way. Okay. But if I want to say it in the nice way, it's like, well, it does take some practice, you know. But all the patterns that you learn is basically the following. If you see partial fraction decomposition, what's that? Okay. If no repetition, then that's easy, right? You see what happened? If no repetition, right? Okay. Now, what happened if you have repetition? Then you repeat the denominator. You see, if you have repetition, x squared, then it's x squared. You have x cubed, something cubed, then that thing squared, that thing cubed. Notice that the repetition case in part B carry over in part D, I'm sorry. Right? If you have squared here and this is not reducible, so you repeat that, right? And keep in mind the numerator should be 1 degree less than the degree of the denominator before you repeat it. Okay? That's basically the principle. Okay? Now, the principle is very brief. The execution is very long. You see, that's why this section, a lot of people just back off after this section. It's just like, no, Thomas, I cannot handle it. You know, but don't worry. This, as I remember, I told you that this section 7.4 will not be in your test 1, right? It will be in your test 2, not test 1. So you have enough time to study. Okay, you have enough time to study. Of course, on the other hand, if you have time to study but you don't study, you waste your time. One way to waste your time is not using it. Okay, you can quote me there and I will be the only person actually ever say it that way. If you don't use your time, you are actually wasting it. So the best way to use your time is basically use it, because otherwise you waste it, right? Okay, our life will not get paused simply because you say I'm too tired. No, even when you rest, time goes on. Okay, time goes on. Okay, let's go on. let's see this question here. I will do partial fraction decomposition. 3x squared plus x plus 4 over x to the 4th plus 3x squared plus 2. The sad thing is, of course, at the same time in this section, you need to know how to factor at least the denominator. Okay, so that's x squared plus 1, x squared plus 2. At least they are not repeating, right? At least they are not repeating. Okay, so something over x squared plus 1, something over x squared plus 2. 1 degree less at the top, ax plus b, cx plus d. Multiply by the LCD. Multiplied by x squared plus 1, x squared plus 2. And I get 3x squared plus x plus 4 equals to ax plus b times x squared plus 2 plus cx plus b times x squared plus 1. Now, again, I told you before that when it comes to level 3 and level 4, I mean type number 3, number 4, you may want to consider using the like terms method. So this is ax cubed plus 2ax plus bx squared plus 2b plus cx cubed plus cx plus dx squared plus d. Then from here we do the matching. You have 4 variable a, b, c, d, so you will need to have 4 equation also to solve that, 4 linear equation to solve that. But hopefully some of them, it's not too hard to do. X cubed term, on the left hand side it's 0, on the right hand side is a plus c. For x squared term, on left hand side is 3, on the right hand side is b plus d. For x term, I have 1 on the left hand side, that's 2a plus c. Actually, we can do something over there. You see, from here we see that c equals to negative a. Right? So 1 equals to 2a minus a equals a. So a equals to 1 and c is negative 1. Right? And then the constant term, oh, by the way, at the same time, don't try to skip steps though. Okay, don't try to skip steps. Okay, organize that. Only on the last couple of steps, then if you want to skip steps, go ahead. But I do not recommend you to do it too early. 2b plus d equals to 4. So d equals to 3 minus b. So d equals to 2. So, what's that again? 3x squared plus x plus 4 over x to the 4th plus 3x squared plus 2 is equal to what's my a? 1x plus b. Let's square plus 1. Let's square plus 1. That's x squared plus 1, and then plus negative 1c plus 2 over x squared plus 2. And now look at the integral. So the integral of 3x squared plus x plus 4 over x to the 4th plus 3x squared plus 2 dx equals to integral of x plus 1 over x squared plus 1. Maybe I use minus here, minus x minus 2 over x squared plus 2. How to integrate each one of them, that's another story. Okay, but I think I will break them up. This is integral of x over x squared plus 1 dx plus integral dx over x squared plus 1, that's tangent inverse x, minus integral of x over x squared plus 2, I will do substitution for that, plus integral of 2 over x squared plus 2 dx. That's tangent inverse also. The more you memorize it, the better. So let's say u1 equals to x squared plus 1. So du1 will be 2x dx. This is 1/2 du over u1. Or you can just use u and w later on. That's time, well, plus tangent inverse of x minus, this is my u2. Different substitution, so I kind of like write it differently. This is 1/2 integral du2 over 2. Okay, plus, I wonder if you remember this. This is 2 times 1 over radical 2 tangent inverse x over radical 2 is constant. What the heck comes? Yeah, memorize it. Okay, memorize that. Integral of dx over x squared plus a squared. Memorize this. This is 1 over a tangent inverse x over a plus constant. Can I just look at the back of the book? If you can use your textbook, right? Now the thing is, how many integral you need to look at the back of the book. If you know that integral shows up a lot, why don't you just memorize it? You see what I mean? Okay, I go on further, then this will be 1/2 natural log of absolute of u1 plus tangent inverse of x minus 1/2 natural log of absolute of u2 plus radical 2 tangent inverse of x over radical 2 plus constant. I need to change that u1 and u2 thing though. Okay, so that's 1/2 natural log of absolute x squared plus 1. You will see our textbook may just use parentheses here because x squared plus 1 is always positive anyway. You see what I mean? Plus tangent inverse of x minus 1/2 natural log of x squared plus 2 plus square root of 2 tangent inverse of x over square root of 2 plus constant. Now you can just stop there, but if I were you, I would go on a little bit further. Actually, I don't mind if you stop here. But I hope you realize that some textbook may put it this way: natural log of square root of x squared plus 1 over x squared plus 2. They combine this guy and this guy together into this. Okay? Plus tangent inverse of x plus square root of 2 tangent inverse of x over square root of 2 plus constant. So we are done with the big portion, the foundation of this partial fraction decomposition. Just the foundation, I'm sorry, but that's the case. I will do more problems. Let's say, for example, number 32. Integral from 0 to 1 of x over x squared plus 4x plus 13. dx. What I will do, I will complete the square at the bottom. It's not factorable. So you can say it's not reducible, but every time it is not reducible, then you can actually rewrite it into something like, for example, here, that is x plus 2 squared plus 9. You see what I mean? And then I will do substitution. U equals to x plus 2, so du equals to dx. And the integral becomes subtract by 2, that's negative 2, subtract by 1. I'm sorry, what am I doing? That's 2, okay. That's 2, this is 3, this is u minus 2, this is u squared plus 9. Okay, now let me continue on the right hand side instead. This is, see, I did substitution, I changed my limit of integration right away. Okay, otherwise you need to bring it back to x. However much you love your x, he is your x. Now it's about you. To integrate this, we have, I think I will split them. Okay, I think I will split them. That's 2 to 3 u over u squared plus 9 du minus integral 2 to 3 of 2 over u squared plus 9. Okay, which will give me, if I do substitution, I cannot use u anymore, use w. So w equals to u squared plus 9, so dw will be 2u du. That's 13 here, that's 18 here, I have 1/2 dw over w minus the integral there, that will be 2 over 3 tangent inverse of u over 3 from 2 to 3. So this is equals to 1/2 natural log of 18 minus 13, natural log of 13, minus 2/3 tangent inverse of 1 minus tangent inverse of 2/3. That's 1/2 natural log of 18/13 minus 2/3 pi/4, minus pi/4 plus 2/3 tangent inverse of 2. And don't need to use calculator, leave it in exact form. Leave it in exact form. Now the 0 and 1 there is just variation, actually nothing much to work on. Okay, but let me show you another method to do this. Right now I will show you a sneaky way to do this. Not that much sneaky though, it's just a new point of view. Number 32, the second attempt. The integral of x over x squared plus 4x, is it? No, not that. Plus 13 dx. Yeah, that's right. From 0 to 1. Take a look, for example, if I have u equals to x squared plus 4x plus 13, what is my du? That's 2x plus 4 dx, right? Let me factor the 2. Then what I will do is I will massage the numerator. I will massage the numerator such that I have x plus 2. So I will do it this way, 0 to 1. I will have x plus 2 minus 2 over x squared plus 4x plus 13 dx, which will be integral from 0 to 1 x plus 2 over x squared plus 4x plus 13 minus 2 times integral, maybe just integral 0 to 1, 2 over x squared plus 4x plus 13 dx. So I split this. This guy goes here, and this guy goes here. But you see, using my substitution, then this will be 1/2 integral. When x equals 0, that's 13. When x equals to 1, that's 18. Right? So du over u minus something. Okay, and we have seen that this is actually 1/2 natural log of 18 minus 13, natural log of 13. You see that? So basically, here's what happened. I saw that the derivative of x squared give me dx, and the derivative of 4x give me constant 4, right? Okay. X squared becomes 2x, derivative of 4x give me constant 4. So I can see that, oh, you know what? I'm missing some term, some constant term here later on. So to play with that, to get that constant term, I add and subtract. So I add 2 because that will make my this help with the substitution. How about the remaining 2, Thomas? Then you separate it. Okay, now I will work on the second part right now, the second term. Do not detach your integration though. Don't detach your integration. Here this is integral from 0 to 1 of 2 over x plus 2 squared plus 9 dx. And then you do your substitution. Right? Or if you want to do it super fast, this is 2 over 3 tangent inverse of x plus 2 over 3 from 0 to 1. See, if you want to do it fast, you cannot do it faster than my method. No way. So instead of skipping steps, how about doing it right so that when I skip steps, you see what actually happened in between. Okay, now then I plug in the 1, then 0, then I will get 2 over 3 tangent inverse of 1 plus 2 over 3 tangent inverse of 2/3. So we get the same answer. Okay, we get the same answer. Those are the sneaky way to do things. I have 8 minutes left. So it seems like on Wednesday, I still need to go over this section here, where I need to teach you from number 39 and on part. Not a lot more, but still necessary. But please learn this, okay? Please learn this. Please study whatever I ask you to do from this section. Because otherwise, after this, you are lost. Number 38, the freaking hard one. X cubed plus 2x squared plus 3x minus 2 equal over x squared plus 2x plus 2 squared dx. The key is you need to complete the square at the bottom. Yes, it is irreducible, but because it is irreducible, then you can complete the squares to be something like this. This is x plus 1 squared plus 1. You see what I mean? And if you can rewrite everything on the top in terms of x plus 1, that would be great. But if not, then you have to find other way. But basically, to do this problem, you need to be very sneaky, very creative, put it that way. Okay, let me try. I wonder if you can follow me. But this is equals to integral on the denominator. it will be x plus 1 squared plus 1 being squared dx. Okay, now what I plan to do is to change this in terms of x plus 1 cube, such that later on when I do substitution, it will be substituted a lot faster. Okay, let's see what is x plus 1 cube looks like. X plus 1 cube is x cubed plus 3x squared plus 3x plus 1. Is it right? Okay, so I can see that this guy and this guy is there. Maybe I write it this way then. I write it this way. This is x plus 1. Oh, no. This is x cubed plus 3x squared plus 3x plus 1. Now, add and subtract such that it's the same to the left-hand side. I will subtract by x squared so that I have 2x squared, right? And then subtract by 3. So this is equals to integral x plus 1 cube minus. Now change that x squared into x plus 1 squared. So x plus 1 squared will be x squared plus 2x plus 1. So x squared plus 2x plus 1, then compensate that. I need to add 2x here. X minus 1 minus 2. So this now becomes, oh, my time is running out. I want to do, this will be 2 times x plus 1 minus 4 over x plus 1 squared plus 1 quantity squared. Now I do substitution by u equals to x plus 1. This should be x squared. Okay, so du equals to dx. So this becomes u cubed minus u squared plus 2u minus 4 over u squared plus 1 being squared. And then you do and then you do partial fraction decomposition. I don't even finish it. Now let me offer you another way to look at that. I don't know if this will work though. Number 38, the second attempt. Integral of x cubed plus 2x squared plus 3x minus 2 over x squared plus 2x plus 2 being squared dx. So I see that on the top I have 3x cubed plus 2x squared plus 2x, and then plus x minus 2. Hans, what are you doing? Because I want to break this up. This is x cubed plus 2x squared plus 2 over x squared plus 2x, I'm sorry, plus 2x plus 2 being squared dx plus integral x minus 2 over x squared plus 2x plus 2 being squared dx. Now, notice that on the top you can factor the x out and one of them cancel. You see that? Okay, plus something. Okay, and then this basically becomes you can make it 1/2 of 2x plus 2 minus 2 maybe, because the derivative of the denominator is 2x plus 2. You see? So that's another way to actually manipulate that. That's 1/2 integral of 2x plus 2 over x squared plus 2x plus 2 dx, and then minus integral of dx over x squared plus 2x plus 2. Don't forget plus the last part there, that's integral of x minus 2 over x squared plus 2x plus 2 being squared dx. Now the first term here will be, it becomes some kind of a scratch paper. I'm sorry, this is 1/2 natural log of absolute x squared plus 2x plus 2. The second part later on, that will be, this is integral of dx over x plus 1 squared plus 1, which becomes tangent inverse of x plus 1. Right? And then plus this integral here. You can do that kind of substitution thing again. So a lot of creativity is required in doing this kind of problem. Okay, but anyway, that's where I will stop. I would like you to do number 13 to number 37. Number 13 to number 37, suggested homework for this 7.4b. So in Wednesday we will do continue on this. So we are not done yet. Okay, see you then on Wednesday.